Looks like we can start. Welcome back, folks. We're just beginning week 3, but probably the biggest announcement we have going on right now is next week is going to be our first exam week. What that means is the exam is officially scheduled for Monday, and we won't actually have a Zoom class. This is going to be kind of just like a pump the brake on the vehicle kind of a day. People might be trying to attend right during the actual class time at 6 p.m. as the testing center is open. And so it also makes sense to not hold class on that day. Plus, it'd be overwhelming to try to get through an exam and new material all at once. We will have ordinary classes on Wednesday at 6 p.m. as normal. But for the other remarks or announcements on the exam, it's going to be just over these 3 sections specifically, keeping it pretty short, just those 3 sections. Also, it'll be a 50-minute exam, so it won't be very long. I'll try to make sure that there's enough time to get through the exam and also check your work. To be prepared for this exam, the most important thing to do is get caught up with the homework. Section 5.1 looks like that one is due September 10th. And even though these are a week away on the deadlines, the best advice for practice or for studying for the exam is try to get them solved as soon as possible, and they'll be the most useful to you. In fact, going across this weekend from week 3 to week 4, my number one objective is to get caught up on grading all homework. So even if you decide to do section 5.2, 5.3, turn them in early, I'll get them graded up, send them back to you so that way you'll know how you're doing on that content ahead of exam 1. You can also take a look into these extra practice exam problems here and here. Version 1, maybe not the most exciting, it's just problems right out of the textbook. And I selected primarily odd problems so that you can check your work in the back of the book. But this is my way of saying from sections 5.1 through 5.3, these are good candidate problems to be prepared for on the exam. Another version you could take a look at, version 2, probably will give you a sense of deja vu. Because what I did with version 2 is I went to the original lecture notes that we're going through, sections 5.1, 5.2, 5.3. I took out some examples and just left the examples that would be good candidate for actual exam problems. So if you go through these problems here, you'll get a good feel for what's going to be on the exam. Also, across the weekend on Friday primarily, and then going into Monday, I did a lot of work on just determining where everyone's going to go for their exam, which testing center and such. And I should have emailed each student to give you some individual instructions, whether it's the Idaho Falls Testing Center, Pocatello Testing Center, or other various testing centers across Idaho or even the nation. If you're not too sure what to do for scheduling your exam, don't hesitate to reach out. Send me a message in Canvas or direct email, drop in during office hours, stay in after class, and I'll be happy to help. But any questions at all, folks, with what we've got going on so far? Okay. Well, another announcement is if I look and sound a little bit off today, it's because I got a cold over the weekend. So this is a lecture with me in the middle of a cold. Good news is I don't think I can infect you across Zoom. It's that bad of a virus, so we should all be safe. But if you need any extra clarifications or if I say something just a little bit weird, I'm going to blame it on the cold, and then we'll double back and fix it. But let's go to where we left off, section 5.2. We did a quick derivation on these notes, and there's another one that I filled in just so that we could save some time and get into a good amount of problems in our remaining time before the exam. But the derivation here was for the Pythagorean identity. Highlighted in yellow because this is one of those critical identities used throughout the semester, just about all over the place in this course. The way it was derived was, we just took the definition of how you define sine and cosine. It's based off the unit circle, x squared plus y squared is 1. So the Pythagorean identity is no different than the defining equation of the unit circle. And on the unit circle, this is our refresher for coming back from the weekend. Once we rotate at angle t in standard position, we take a coordinate on that one specific circle, radius 1, center of the origin. The x-coordinate of this terminal position and the y-coordinate determine both cosine and the sine functions. So x That x specifically on the unit circle is literally cosine of the angle t. Y is literally sine of the angle t as well. So the input to the function is t, whether we put those parentheses in or not. And the output is coordinates, so kind of an unusual function. That means wherever we saw x, we could put in cosine. Wherever we see y here, we can put in sine. And that's where this identity up here came from. Example 2 is just taking a look at how you might use this identity. But any questions about it before we give it a try? Okay, let's jump into example 2. Let me scroll to where we can still see the identity. There we go. Example 2 is kind of a wordy one, but it's one of those problems where if you read through this and just draw as you read, then you get a good feel for what's going on. A lot of problems in the textbook look like this. So this is a good practice as well to help prepare. It says, let the point xy, p of xy, denote the point where the terminal side of angle theta, might as well use color coding at this point, in standard position meets the unit circle. We're also saying, suppose that point P is in quadrant 3, and we're given a y-coordinate of negative 5/13. So here's what this all looks like so far. Maybe a little bit more like this for the angle drawn. Doesn't have to be perfect, but try to do your best you can on drawing it. Here's the angle theta that was given. Other bit of information was the y-coordinate right here. Oh, that's probably not good color coding. We used green for a different purpose. Let me use this for just highlighting then. The y-coordinate right at this point here is at negative 5/13. So that height is negative 5/13. The problem says use this information that's given so far to calculate both sine theta and cosine theta. And just for the sake of color coding, let me actually redo this color coding here. Let's try to keep everything the same. I'm going to blame this on the infection I contracted. Thinking just a little bit harder today than normal, and it's not easy normally anyways. So there's the y value. Y coordinate goes with sine. We want a cosine value. And that's the y coordinate that was given us, that they were giving to us. So we rotated theta. We ended in quadrant 3 here. Y coordinate's negative 5/13. And all we need to do to finish this problem is say, what does sine of theta, either with or without parentheses, equal? And what does cosine of theta equal? Well, the first one's kind of a giveaway, right? They tell us that the y-coordinate is sine theta. For the definition up here, that's exactly how sine is defined for any angle t or theta. So sine theta is negative 5/13. And that's excellent. That means we're now halfway done. If we can get the cosine theta value here, our work is completely over on this problem. Not sure where I was going with that dashed line. Let me maybe do it this way. Any questions or comments so far? Okay, now getting cosine is trickier, right? We could visually estimate and say it's some number here where the red dot is, but we need that exact figure. We don't want to guess, round, or anything like that. So that's where the Pythagorean identity up here comes in play. Cosine squared plus sine squared equals 1 gives us an equation now, because if you know the sine value, you can use that information to solve for the cosine value. So let me start just by writing it down. Cosine squared, the angle here this time is theta, plus sine squared of theta equals 1. We can put in a substitution right here already, and it would look like this: cosine squared theta plus sine squared. The power 2 here becomes an outer exponent, and sine theta itself gets substituted in for the negative 5/13. Notice the way you write this in is really critical, actually. Power 2 is going to negate the negative sign. Negative times negative is positive. But that only works algebraically if you put parentheses around like this with a negative on the inside. Right-hand side is 1, so simplifying, equation's now that cosine squared theta plus square of 5/13 is 25 169ths. Right-hand side we want to write as a fraction, 169, 169. Weird way to write that fraction, but now just subtract 25 169ths from both sides. Running out of space, so I'll use the arrow strategy. Cosine squared theta is now equal to 144 169ths. So now, last step to take here is square root both sides. But depending on how rusty or how sharp you are with this algebraic step, it could be kind of a dangerous one. Let's put down just a warning. Keep in mind that if you have anything that looks like this, square root of a squared, a for anything, doesn't matter what a is, the result is the absolute value of a. So this is just a generic formula. That's a way you can define absolute value. There's loads of ways to do it. The way this comes into play over here is if you take the square root of both sides of this equation, you have that cosine theta equals positive or negative 12/13. So we don't put in absolute values in this equation, but it comes in as a plus or a minus. So now it's up to us to decide. There's only one unique answer to this. Has anyone spotted if this will be positive or negative in our answer? Good news is we have a 50-50% chance, right? It's like kind of like plugging in a USB blind without checking the port too carefully. But the quick way to know for sure is we just go back over here to the unit circle diagram. It seems weird why we draw these sometimes because we may not feel like we always need them, but actually this was really critical. Or if you have a really good mental chalkboard and you can just visualize all this in your head, some people can, then when it said P is in quadrant 3, that was just telling us that the cosine value up here is negative. Let me change the color on this. Cosine is whatever this x-coordinate is, and because it's on the left end of the x-axis, cosine is negative. So that means back over here, we pick the negative sign. Cosine theta has to be negative 12/13. It can't actually be the positive one. We can write up here as well just to finish that off, but that's now optional. Once you say it somewhere on your paper, you've got the answer. But just because my work is now everywhere, let me box out. All we needed to do to solve this was state this sign for sine and solve for cosine. When doing this in homework, you do have to show your steps. But if you make any mistakes when you do this as a homework problem, I'll let you know where it was to help you prepare for if this comes up as an exam kind of problem. Any questions at all, folks? Getting that negative 12/13? Okay, well, we did it. That's one of the typical use cases of the Pythagorean identity. The next section, we're going to have cotangents, tangents, secants, cosecants, and two more identities just like this one. But for the moment, next thing we want to do is kind of expand on what we did over here. We were calculating sines and cosines of various different angles, but we were pretty restrictive on what we were calculating on, just multiples of pi over 2, going around the unit circle there in 90-degree increments. The angles that we really are interested in look a lot like these ones. Either open common angles in radian measure, or you can go to the 5.1 notes where we hand-drawn a few. Let's go to our hand-drawn ones. I encourage you to practice this as part of like a warm-up before you do homework, before you study, because knowing where these angles are critical to really getting good at calculating the sine and cosine functions. The trick is, if you know where information is on this first quadrant, you can now extrapolate to all the other ones. So there are some really big patterns here that we're going to highlight. And even though the exam is closed notes, I am going to provide this table. So we'll use this table as we go. Take a look at it as you're doing the problems and homework. If you're solving your homework problems like we're doing in these notes, using this table, and practice memorizing this chart right here, you're going to be in great shape. The exam isn't going to go too far into the various problems. It's going to be more about doing these kinds of evaluations in sections 5.2, 5.3. First, like I mentioned, I did skip this derivation. Well, we didn't skip it. It's still here on paper. But I decided to solve it not in class, so I didn't take too much of our time on doing various derivations. First things first, we want to get really good at using this chart. So let's maybe practice what this chart is saying just to start out. If we're on any row of this chart, its angle measurements 0 radians to pi/2 radians. Again, that means we're from 0 here all the way up to pi/2, the first quadrant of the unit circle diagram. And this tells us just about everything we need to know. These are the numbers that show up over and over and over again. 0.32, it's nice to know, root 3 over 2 is nice to know it's about 0.9, so that when we plot things, we know that's pretty close to a 1. Root 2 over 2 is pretty close to a 0.7, so when we go to plot that, we're like 3/4 in, around 0.75, just a little shy. Now, if we focus on any row, say just this one for an example, what it is saying is that, let's take a look at pi/3, that's the input to sine. And so we can say sine at input pi/3 is equal to root 3 over 2. So that's what this table is saying so far. If we look into cosine at that same angle pi/3, it's telling us that cosine at pi/3 is equal to 1/2. And if you drew a unit circle diagram to go along with that, let me insert some, can't insert space that way. Let me insert some space this way. We drew in a unit circle diagram to go along with this thought. It would look like this. So we rotate by an angle measurement pi/3. That's going to be out here, 60 degrees. That was part of our goal with the last section, 5.1, is just to get familiar with these angles. But then once we're right here, the x-coordinate is cosine. Notice just by my hand-drawn sketch, and it's not a perfect sketch, that looks like it's a half. It's about halfway from here to here. Sine at the rotation pi/3 is whatever this number is. But notice how it's pretty close to 1. That is your dead giveaway. It's exactly root 3 over 2. So we'll practice doing these kinds of evaluations for not just these angles, but for other angles on the unit circle diagram. And that's part of what this derivation was all about. Where did people come up with the numbers root 3 over 2? How do they know it's that exactly? How they come up with 1/2? Well, the reading shows some derivations you could look into. And the notes that I filled in so we didn't take too much time just show how to derive it for pi/4. It turns out that sine and cosine at pi/4, let me fix my color coding there, match up exactly to a root 2 over 2. So this on the left is how we use this kind of table. And our eventual goal is to use that table to help us evaluate any one of these angles you see here on this diagram. First, if you are interested, let's just take a quick look at that derivation, and then we'll go into some of those bigger problems. But I should call out first, any questions whatsoever with this table or the evaluation on the left? Okay, so quick rundown on what's going on here is, if we want to derive sine pi/4, cosine pi/4, first thing I did was put down this line, y = x. Reason for that is Y equals X is the pi over 4 line that comes through like this. 45 degrees gives us exactly the line Y equals X. Then once you have that, something kind of magical happens, because if you build a right triangle, this one right here, out here is the same right triangle, it's just magnified, then you can use the fact that this distance this way is X. So we draw an X down here. Distance this way is Y, the vertical Y coordinate, but this distance Y gives us a height Y over here, yet Y is X. If Y is X right here, then at the same exact time, don't want to Control Z too far. At the same exact time, we have Y equals X right here as well. So any point that's set, if we're on that point where Y equals X, everywhere on page Y occurs, we can just put down an X. The next big thought was, how do we get a 1 here? Well, we knew the radius automatically because it's implied implicitly that it's a unit circle diagram, so the radius was exactly 1. So this kind of derivation only works for pi over 4. To see what happens with pi over 3, pi over 6, you have to do some other similar kind of argument. The reading does a great job showing how those go. But once you have all this down, just use the ordinary Pythagorean identity, a squared plus b squared is c squared. So I threw in this x down here, squared it, threw in the x here, squared it. Solving it all the way back down gives you, upon rationalizing the denominator, x is root 2 over 2. If that's what x is, so is y. And then at the same time, cosine is the x coordinate, it's root 2 over 2. Sine is the y coordinate, it's also root 2 over 2. And that's how we got these values right here for pi over 4. It comes out to the same exact values because on the 45-degree line, y is x. The values have to be the same. So some people love seeing this derivation because it shows where these angles come from. This is a fast way to look at it. But another thing that's nice about it is it's something you can draw and actually just reason through by doing these kinds of problems, Pythagorean identity. But even though it's an official example, this is not something I would ever ask you on an exam. These are more just so we can connect the dots on some of these concepts before we try the main problems. Well, we're going to be using this table a lot, so the next problem is just practicing some more of these kinds of evaluations. First, any quick questions at all on the derivation? Well, any questions at all, they don't have to be quick. Okay, well, we're just about done with these notes. This is kind of a shorter section. Section 5.3 is just a touch lighter, or touch bigger, I would say. We want to evaluate the following problems using reference angles. And this will be, again, like I mentioned, a big part of the third exam, doing these kinds of evaluations, just like we're about to do. The new concept is reference angles. And what we mean is these 5 different angles you see here, from 0 radians up to pi over 2 radians, gives us essentially everything that we need. They're the references that we use to evaluate both sine and cosine. These are the right numbers, except one thing is missing. You might not know if it's going to come out as positive or negative with this, unless you know where is 5 pi over 4 on the unit circle. If you know where that is, the fact that it is a pi over 4 tells you sine is going to be either positive root 2 over 2 or a negative root 2 over 2. So this table actually gives you a lot to work with on the exam. We just need to know how to use a reference angle strategy, which means you have to be familiar with these key angles that we see here. So this is the major memorization, I would say, for upcoming exam 1. So let's give this a try. I'm going to copy this down so we can scroll with it along the way. I was doing this as a problem on either homework or an exam. This is pretty much how I would start off each and every one of them. And really the goal this semester is by the time we're like on week 12, week 14, maybe preparing for the final exam, you see this and it's basically just automatic. You know the value. If you already know the value, then good on you. This might be kind of boring, but this is the process. First thing we do is we've just put down the unit circle. And we pay a lot of attention to that denominator there. Make sure the fraction's reduced. So if this was, say, 4 pi over 4, I wouldn't be worried about that denominator anymore. I just reduce it to cosine pi. But with the denominator of 4, first thing I would do is put down pi over 4 right here to match up that division by 4. We know a lot about pi over 4. For example, the sine value from the derivation above is whatever this number is. Because we're dealing with sine, let's keep that color coding going. And we have a pi over 4. We're expecting the value root 2 over 2. It looks about right. That's about 0.7. So root 2 over 2 is what I would put right here on the diagram. However, it's not the answer. It's either going to be, well, I shouldn't say it's not the answer. It's not guaranteed to be the answer. The answer appears either positive or negative root 2 over 2, and we need to spot it. So here's where we start putting down the pi over 4s. This is pi over 4 going this way, 2 pi over 4. Over here in the middle, this one is 3 pi over 4. 4 pi over 4 gives us pi reduced. 5 pi over 4 is here, so we stop. If all you did is put down 5 pi over 4 right here on your diagram, that's fantastic. That would tell me you've got a lot of practice. You have a good understanding of where these angles end up. They're just literally counted off in that way by odds. Now, down here at 5 pi over 4, what we need to solve the problem is that number there. Sine is the y-coordinate. There it is on the y-axis. It's now guaranteed to be negative, being on the lower end there. So now that tells us it's negative root 2 over 2. And all we need to do to answer the question is come back here and say equals negative root 2 over 2. And just to emphasize, because this would be not great to forget on the exam, you could lose some points. This is the answer. And this is just the work on getting us there. We use this reference table, root 2 over 2. Recall we said that that's about 0.7. This didn't look like a half. It looks like it's about 0.7. And so that's another way we know root 2 over 2 is coming up. Well, that's one down. Any questions, folks, on doing that evaluation there?
So for any pi over 4, uh, the sign would always just be root 2 over 2. And then to know for if it's positive or negative, you just look at the diagram.
Exactly, yeah. So just a related problem just to go right along with it. Over here is 7 pi over 4. And so if we said do maybe a cosine 7 pi over 4, what will we do then? Well, we know cosine at the reference angle pi over 4 gives us this root 2 over 2 over here. And yet, if we're at 7 pi over 4, right at this location, cosine is the first coordinate, the value on the x-axis. So this one would be positive root 2 over 2. Orange just to say this was just additional information on that problem. But does that make sense so far?
Yeah, that makes sense.
Awesome.
It's a lot more
This,
simple than it looks.
yeah, I hear you. When you look at it all like this, just all the information at once, I think it does feel like a lot of details, but just track it through the diagram being built bit by bit, and it's just a process that you get familiar with over time. Well, let's try out another one then. Cosine negative 5 pi over 3. This one's a little bit weird because now it's a negative rotation, so we have to be mindful of the direction we rotate. So let's start off with this before. I'll just put the unit circle over here this time, hopefully out of the way. Pi over 3s are kind of tricky. Let's go back to the sketch over here. Pi over 3s are the ones that are closer to the y-axis. They kind of look like this. They form this shape here. And the way we write them out is, notice up on the numerator, or not numerator, but the top part, it goes 1, 2 pi over 3. On the bottom part, it goes 4 pi over 3, 5 pi over 3. In other words, the evens are on the left-hand side, and the odds are on the right-hand side. So that's one way to think about it. So now going back over here, if we're going in the negative direction, now just imagine this whole thing just flips over like that. So flip the paper, imagine where those angles fell, and you're going in the right directions. So let me write them out. It's going to seem kind of silly at first if you see where it's going to end up. First, it's negative pi over 3. We rotated clockwise 60 degrees. We end up there. Negative 2 pi over 3. We end up there. Negative 4 pi over 3 ends up here. And negative 5 pi over 3 ends up there. Pause on that picture just for a moment, just for emphasis. Once again, it should look like just this, except it got flipped around. So the 5 pi over 3 went above, 4 pi over 3 went above. Now they have negative signs and so on. I wonder if we can flip that. That's not easy to look at, so maybe not valuable to actually flip it. Once we're there, we make a key observation. Well, negative 5 pi over 3, this is almost like the silly part of this. That took us to a position which is right at pi over 3. So if you wanted to, you could say cosine negative 5 pi over 3 equals cosine pi over 3. It's a totally optional step. You could just give me the number right at that point, but it's nice to see. It goes along with the comment from last class where folks remarked, there's lots of ways to write that angle that gives us that terminal point right there. Negative 5 pi over 3 is one way to do it, but it's kind of inconvenient. It looks more complicated than it needed to be. Pi over 3 is just as well. If we go with pi over 3, well, we just go cosine at pi over 3 is 1/2. So it should be that number there. My drawing is not super believable, doesn't quite look like 1/2, but certainly didn't look like it was 0.7 to the right. It didn't look like it was 0.9 even further to the right. So, this is about in the right ballpark, or right around 1/2. If I drew that more carefully, it probably would have looked a little bit more believable. But this is kind of a strange looking circle here. I think also my angle looked like it was probably more like 70 degrees than 60 degrees. But again, with the understanding that things are hand-drawn, drawing this out gives you a really good idea where things end up. Even if I didn't have this table whatsoever, I would have probably guessed 1/2, and that would have been exactly correct. Well, that's handling a negative angle, kind of an interesting problem. Any questions, folks, finalizing this one? Okay, let's try out another one for the extra practice. In the next section, we're pretty much going to be starting off doing a bunch of these, but we're also going to define the additional trigonometric functions. So if this seems kind of foggy and vague so far, we're going to be practicing it a lot, pretty much all week. This is the main problems we're going to be taking a look at. So part C says do sine at 7 pi over 6. We're taking the reference angle approach, so the denominator there is critical. 7 pi over 6 is much like a pi over 6. So we're expecting either positive 1/2 or negative 1/2. Knowing exactly where 7 pi over 6 is going to do the job for us. Sometimes I think pi over 6s are a little bit easier to nail down on the unit circle. Let me show you why. The nice trick here is, here's pi radians, 180 degrees. But pi radians, if you really wanted to, you could call 6 pi over 6 radians. That seems silly, but it's helpful because if you're at 6 pi over 6, and you want to go just 30 degrees further, you literally just add pi over 6. Add pi over 6, and you end up at the 7 pi over 6. Here we are. And that's exactly where we want it to be. So that's the terminal position, 7 pi over 6. Likewise, with the same idea, here's where 5 pi over 6 would be. Similar ideas, if you call 2 pi rotation 12 pi over 6, it might help you remind you that this is 11 pi over 6 in this location, just 60 degrees shy of one full rotation, the 12 pi's over 6. So whatever kind of numerical little game that can make things make sense is actually a humongous help. There's other little games here you might notice. There's a whole bunch of patterns that I might not have seen that you saw. The more you stare at this and practice just drawing it out, the more you see where things fall. It's kind of like practicing your multiplication charts from elementary school. Rote memorization is not the funnest thing in the world, but sometimes it has its importance. And in this case, this is one of those times where we really need it. Keep practicing this out, and really probably by the third time you start writing down that unit circle with good practice, it's going to start coming together really nicely. Then the major thing that was new in this section is if you're doing a sine function, it's the second coordinate, which means the coordinate on the y-axis. So wherever that terminal position was, that's the hard part. The easy part is just to get that number. And again, imagine that table is just gone and you're guessing. The best numerical guess you would probably all give is, looks like negative 1/2. Negative just because it's below the x-axis now. But the reference angle approach says you can double check the table. Using pi over 6, because we have a denominator 6 here, comparing against sine, you are expecting 1/2. The only thing we didn't know is whether the answer would be positive or negative 1/2. So the moment we slap it with negative 1/2, our work is done on that. It's strange because if you're doing this as a homework problem and you just tell me sine 7 pi over 6 equals negative 1/2, I'll accept that for full credit. Same if you did that on an exam. I'm just going to assume that you're really familiar with this kind of approach, or you have a really good mental image and you didn't need to actually write it down to do the computation. If you're learning it for the first time, this is the best way to really get to that point where you can just look at it and say, I know it's negative 1/2. Here's my answer. Practice drawing these out, practice drawing where the angle terminates, and then just tell yourself if it's sine, it's that coordinate there. If it were cosine, let's add just a quick comment. If it were cosine, it would be whatever that number is. That one looks like it's pretty close to negative 1. So I would have said root 3 over 2 on this one. Cosine 7 pi over 6 is root 3 over 2 exactly. So the other reminders on the notes is, keep in mind, root 3 over 2 is approximately 0.9. Root 2 over 2 is approximately 0.7. And that just helps to plot things out, because right where the red dot is approximately 0.9. If you draw a circle and the angle terminates, giving you that coordinate, that looks like about approximately 0.7. And the negative 1/2s, positive 1/2s are the easy ones to spot. We did it, folks. That's the conclusion of these notes here. Any last questions about section 5.2?
I do have a question.
Yeah, go ahead.
For the cosine example that you did, would it be negative square root of 3 over 2?
Thanks for spotting that. I would blame that on having a cold, but I think that was just a complete oversight on my point. Thanks for spotting that, David. It's
No problem.
over here on the negative end of the x-axis. It's got to be a negative root 3 over 2. Good eye on that one. It deserves some huge emphasis. And it's a big deal because, for this as a trig problem, that negative sign, even though we grade on partial credit, it's worth a good amount. That could be an entire point on a problem. An entire point on the problem could really move your percentage on the exam. So watch out for the positive negatives. They are actually quite vital on these problems. Thanks for spotting that again. Other questions so far? Okay, well, that critical connection put in, let me save these notes again. And now for the next exciting thing, well, we're doing the same stuff, except we have 4 more functions we're going to take a look at. Not as bad as it sounds, we just have to formally define them once and for all. Really, section 5.3 and 5.2, they could have gone together, but the book tried to separate them out so it's not too much information all at once. And here's how pretty much all the notes start. It says, the terminal side of an angle T intersects the unit circle at a point xy. We define the 6 trigonometric functions in this way. So once again, it's all about the unit circle itself. We'll start by drawing that out. That's not my best work, but we're going to go with it. When we say unit circle, just as a reminder, we mean x squared plus y squared equals 1, which is the equation of that circle. It's talking about the terminal side of an angle T, and we're taking for granted at this point in the notes, we automatically mean measured in standard position. So the positive x-axis is the initial side. The terminal side for a rotation T, I'll just put it in quadrant 1 to make a simple diagram that doesn't get too busy. So here's the terminal side here, and we have a point xy. There it is, x and y. The last section was to help us get used to the concept that cosine at the angle T is x. So that's our cosine function here. And sine angle T is y, so that's our sine function here. So these were the 2 major things we were looking at in section 5.2. And now we add a whole bunch more functions, so we are tripling the list we had from before. It seems kind of unfair. But you know what? The good thing is there are some major patterns here. Let's start off by the column system. On the left column, I have 3 fundamental functions: sine, cosine, and tangent. Notice that tangent, excuse me, is just the ratio of the y-coordinate divided by the x-coordinate. So in other words, well, if y is sine t and x is cosine t, another way to define this is to say tangent at angle t is just the sine function divided by the cosine function. Then a whole bunch of more information on the right, but here's our pattern. These ones on the right are the reciprocal functions. It's a fancy word. Reciprocal just meaning we're literally flipping the fraction, or excuse me, yeah, sometimes it's a fraction. We're flipping the thing on the left, not a fraction here, but make it a fraction in your mind. Y divided by 1 is still y. And we get the reciprocal function on the right. So sine at t is the y-coordinate. CSC stands for cosecant. Cosecant of t is 1 over the y-coordinate. Likewise, cosine of t is the x-coordinate. Secant, or SEC, at t is the reciprocal of the x-coordinate. And likewise, tangent is y divided by x. Tan is just shorthand for tangent down below. So cot, no harm done if you say cot, but cot really means cotangent, is, again, just flip the fraction, x divided by y. So these are the core definitions, how we define them from the unit circle. But I would say the better way to think about these, more useful to algebra and the things we'll do in class, is seeing it this way. It's the same exact information, but this is more important as formulas. In other words, this table is great. It tells us how to define cosecant, secant, cotangent, and tangent. But if you're actually going to calculate any one of these 4 values, this is the better way to think of it. This is how you're most likely than not actually going to calculate. And that means everything we did in section 5.2, calculating sines and cosines, we just bring it to the table on this one to calculate all of our new functions. So the major thing to memorize on these notes are, how do we define each one of these 6 different functions. Again, the organization here is actually really, really critical, because if you always think of cosecant and sine going together, you'll know how one relates to the other. Cosecant is just to divide by sine. Secant is just to divide by cosine. Tangent is sine over cosine. So the co-function, cotangent, is a reciprocal, cosine divided by sine. Sometimes one way that's helpful to memorize this is notice that cotangent has cosine in the numerator, so co to co is a great way to memorize that there. This is not the greatest pattern though. Cosine going to a secant and sine going to a cosecant is tougher to describe why the naming goes that way without a right triangle. Excuse me. But in section 5.4, we will get to that right triangle to give some more inspiration of why we named the functions that way. Down below is just a chart to say what are the full names if you had to write it down. If you had to write a letter to cosecant, what would it start as? And so that's the actual name of the function. Sorry, my voice seems to be giving out a little bit at the moment. But any questions so far, folks, with just how we define these functions? Okay, next thing we want to try out is just doing some evaluations. And that's what we're getting into down below on these notes. Let me see if I still have that. Yeah, I do. So the exam, we'll have this printed out in one part inside the exam, so you can use this as reference. The thing that's tricky here is for calculating tangent, we have to know, well, how is it defined in the very first place? Recall cotangent would have cosine in the numerator, divide by sine. So it's one great way to think about it. That means tangent 11 pi over 6 will have sine in the numerator. Sine at 11 pi over 6, divide by cosine in the denominator. So cosine at 11 pi over 6. So that's how we start out. There's more to the story because we still have to calculate it. But this is essentially the entire new thing so far on the notes in section 5.3, that tangent is just the ratio of sine divided by cosine. Next thing we do is just evaluate that. Go to the unit circle. One trick is, we mentioned, 2 pi goes here, which is 12 pi over 6. That relates the pi over 6s that we see here to these values here. So we're using the reference angle approach. 11 pi over 6 is just 30 degrees short of the full rotation 2 pi. So it terminates right here. Then we can read off the values. Sine is going to be whatever this value is. Don't forget the negative sign as I did in the other notes. That one's -1/2. Cosine is whatever this value is. Harder to see, but if it's close to 1, that's √3/2. But notice, we grabbed those values. We just had to modify this one, because if we're in quadrant 4, we pick the negative sign. Then we do a bit of algebra from this point on. Sine is in the numerator, and it is the y-coordinate here, -1/2. I don't know why I made that fraction so long, but let's roll with it. Cosine in the denominator gives us the x-coordinate, the first coordinate, √3/2. And we just have to simplify that fraction. Loads of ways to do it. You could just go like this. Division by 2's would cancel off immediately. Some people might want to do it with an extra step of going -1/2 times, take the reciprocal of the denominator, 2/√3. They cancel here just as the same as they would have canceled in the prior step. And if you give me the answer, -1/√3, you've got it. That's a terrific answer. However, if you looked at this answer, say you're doing homework, and you check the back of the book, you might be concerned because the back of the book does one other thing, which is a little annoying in trigonometry. We rationalize the denominators. In fact, everything in this table, like the √2/2's, for example, have been rationalized. That's 1/√2, but for some reason, we like this number better. You're always welcome to leave it like that on a homework or an exam problem. But in the notes, I'll often take this additional step because people tend to want to rationalize the denominator just to check their homework problems to see if they're correct. So that involves multiplying by root 3 over root 3. Across the denominator, it was irrational, but root 3 times root 3 is 3. Now it's rational. We've rationalized it. Numerator is negative root 3. And that's where that problem would end there. It's a little bit longer because notice the arithmetic took more work than the actual algebra on the left. But that's how problems like these are going to go. We'll practice many more when we come back on Wednesday. Hopefully I won't be feeling as sick and having my voice give out. But any last questions at all, folks, with where we ended at today? Okay, well, have a great night, folks. Try not to get sick. It's kind of turns out it sucks, I've learned. And I'll see you all on Wednesday. Take care. Thanks, folks. Appreciate it.